Hi, and a very good day to you, Prof. Dr. Ho Wai Shin. So today I would like to present the process control lab proposal for flow control for our group group 5. In introduction for background of experiment, flow control is a vital industry for efficiency, safety, and maintaining production quality, and it regulates the flow of materials of fluid in processes like chemical, oil and gas, and food production. And for the PID control like proportional, integral, and derivative, it actually widely used for feedback control in flow system. And for the example, proportional control, it will correct errors based on the current conditions. And for integral control, it will eliminate steady state errors. And for the derivative control, it can reduce the response time and dampen oscillation. And we have also the tuning methods like Ziegler-Nichols and Cohen-Cohen adjust for PID's parameter for optimal performance. So the Ziegler-Nichols, the methods is practical but can be aggressive. And for the Cohen focuses on smoother step responses. And for the software tools, we have two software tools that we will use. For the example, MATLAB Simulate, it for simulation and transfer function modeling. And we will also use LabVIEW, it's for real-time PID tuning. Okay, so for our objective of the experiment, the first one is to investigate the impact of the NPI and PID controllers on the process response curve in a flow control system, and the second one to compare and differentiate the effects of offline and online tuning methods within both a pilot plan and MATLAB Simulate. And the last one is to assess and compare the performance of the flow control by evaluating the behavior of different PID modes and tuning parameters. Okay, for our scope of experiment is to conduct an experiment on a flow control system using a pilot plant and MATLAB Simulink to identify the most effective control strategy. And second one, to evaluate offline and online tuning techniques by applying small set point changes and analyzing the resulting system responses. And the third one is simulate the flow control system using MATLAB Simulink after determining the key parameters such as process state, basic, integral time constant, tau, and derivative time constant, tau d, and prove the experiment.
Hello everyone, I'm going to continue with the literature review. My name is Nur Insyirah binti Ismail and I will be explaining about the literature review. So first of all, what is flow control? Flow control is actually, what does it mean by flow control? It is actually regulates the flow or pressure of fluids through control valve, and it is sorry, it is also a critical process to control in chemical, oil and gas, and also the food industry. Last but not least, it also maintains safety, efficiency, and also production quality. As you can see from the first picture here, we have a industrial process with control valves. Sorry. Next is an overview of PID control. What is PID? Well, it's actually proportional integral derivative. There are three parts, which is proportional control, which is it reduces current error but cannot remove steady state error. And secondly is the proportional integral control. It corrects the steady state error but slower the response. And last but not least, which is proportional integral derivative control, which is what they usually use in the industry. It combines all three actions for fast, stable, and more accurate control. That is why we use most industry use PID control. Next, for the literature review, we will go into the open loop versus the closed loop control system. So, what is open loop? Open loop is actually no feedback operates on the set point, and then for example, we can use like washing machine, dishwasher, and the advantages of the open loop control is it's simple and it is cost effective. However, there are some limitation to it, which is it cannot correct deviation from the set point. So as you can see from the picture here, for the open loop, it's like the input, which is also where there's the input, sorry, and then controller, and then control signal straight goes to the plant, and then there's an output. However, for the closed loop control, it incorporates feedback to self regulate and it uses more complex dynamic processes. For example, is like automated control system in chemical plants. And from the picture below here, as you can see, the X part, the circle X part area detected is also actually the set point. And then we have a controller here, and after the controller we have an actuator. So the actuator is the um, where it changes based on the sensor and the feedback elements, and then after that we go to the plant, and then if there's any deviation from the control variables, the output that we want, the sensor will send it and then it gives the feedback signal to the set point, to the error detector, and then that's it will go on in a loop. That's why it's called a closed loop control system. Next is tuning methods for PID controllers. So there are two types of tuning methods, which is Ziegler-Nichols method and then Kohn-Kuhn method. So Ziegler's method is actually used for an online tuning, meaning that uh, it focuses on obtaining ultimate gain, which is the KCU and the ultimate period. So the advantages of the Ziegler Nicholas is that it's effective, but can produce aggressive responses. Hence, it's take a longer time for it to stable. The second method is Kuhn method, which is an offline tuning using manual step response analysis. And then for this method, it produces a smoother system behavior but requires manual adjustment. So, this is the table for how to find the KC, the tau I, and tau D for each of the controller. Okay, so we can use, there are software tools for PID implementation. We can use MATLAB Simulink. It simulates and visualizes control models for tuning. And then we can also use LabVIEW that allow real-time PID tuning through interactive controls. That is all from me. Thank you.
Hi, my name is Ahmed Shafiq, and I will present about the methodology of the experiment in startup procedure. First and foremost, the apparatus that we are using for this experiment is flow control pilot plant. So for the startup procedure, the first step is we fill up the TN1 with sufficient water until approximately 80% full and set all values according to the initial position outlined in table 3.1 as you can see at the right bottom of this slide. The third step is we supply compressed air, which is 5 bars, and ensure that the air regulator has been set to 1.4 bars, and check the RG1 pressure whether it is correct. And then we turn on the instrument power supply and turn on the computer, and also turn on the SE102 flow control diagram software. And then we click the keyboards menu to log in and then press the enter button. For the 10th step, we open the trend view on the left side screen and open the controller F1C1 on the left side screen. And we need to set to manual mode and also set the MV to 100. The 14th step is turn on the pump P1 by pressing the start button at the control panel. And then we click the default button at the vertical box menu on the right side screen. On the 16th step is click the vertical zoom in and zoom out box menu to adjust wide scale, and click the horizontal zoom in and zoom out box menu to adjust add scale. And the last one, we can start the experiment after entering all the controller parameters.
A very good day, I'm Dharma and today I will explain on the methodology for both open loop flow control and closed loop flow control. So for open loop flow control, we'll be using the Cohen-Kuhn tuning relations. First, we have to ensure that the process is in a steady state. The MV value Kc is set to a small value, for example 1.0, and the controller is set to a manual mode. After the system reaches steady state again, a small momentary set point change is introduced to drive the control variable away from the set point. Then we can calculate the PID controller settings using the Cohen-Kuhn tuning relation in table 3.2. Next, we can evaluate the Cohen-Kuhn setting by introducing a small set point change, and we have to observe the open loop response. Finally, we can obtain the F4PD transfer function for the flow control system using the data gathered from each of the P, PI, and PID controllers. Next, I will be explaining on the methodology for closed-loop flow control, which we will be using the Ziegler-Nichols tuning relations. First, we have to make sure the process is in a steady state. Then set tau d to 0 and tau I to the largest value possible to eliminate the integral and derivative control action. Then set Kc to a small value, for example 1.0, and switch the controller to automatic mode. Introduce a small momentary set point change to drive the control variable away from the set point. Then increase the value of Kc gradually in a small increment until continuous cycling occurs. The value of Kc that produces continuous cycling is known as the ultimate gain Kcu, while the period of corresponding sustained oscillation is called as ultimate period Pu. Calculate the PID controller setting by using the Ziegler-Nichols Zn tuning relation in table 3.3. Finally, introduce a small set point change to evaluate the Zn controller settings and observe the closed loop response. For the shutdown procedure, first we have to switch off the pump P1 by pressing the stop button on the control panel. Secondly, click the exit button. Next, we have to shut down the computer and finally turn off the main power supply.
Hello and very good day to doctor. So my name is Iqbal. So my part is to explain the expected results from the experiment. So we can from the experiment we can expect from the closed loop flow control from the Ziegler-Nichols tuning. And for the P controller, we can expect that the system will react to error, meaning that the difference between the actual value and the set points is based only on the proportional gain. For the response, the system will respond quickly but may still have some state error, and it might not reach to exact set point. For the oscillation, so there will be a faster response to change, but it may result in some small oscillation. So for the PI controller, we can expect the system will now react to error based on the both proportional gain and integration. For the response, the PI controller will correct steady state error better than P controller alone, meaning it can bring the system exactly to the set point without leftover error. And for their oscillation, they may still be small oscillation, but they should die down faster over the time. And for the PID controller, we can expect the PID controller use all three parts, which is proportional, integral, and derivative. For the response for the PID controller, we can expect this will result in the fastest and smoothest response to the change, as it not only react to the current error but also predict future trend, which is derivative, and correct past error, which is integral. So for the oscillation, so the system should settle down more quickly with less overshoot and fewer oscillation, leading to very smooth control. So summary of expected result. So based on this table is P controller is fast response but some steady state error and oscillation. For the PI controller, they more accurate with less error at the set point and better control, but may still have some oscillation. And lastly, PID control, they more precise with faster settling, minimal oscillation, and less overshoot, ensuring the system reach the set point quickly and stay there smoothly. So for the next expected result that can we expect from the open loop flow control, which is Cohen-Kuhn tuning. So for the P control, we can expect that the system will react quickly to the change, but won't eliminate any steady state error completely. For the oscillation, it may show some oscillation, especially if the process has longer delay, but they should be moderate. For the PI controller, for the response, the system will now handle the steady state error more effectively, bringing the output closer to the set point without drifting. So for the oscillation, it should have a reduced oscillation, and the integral action will help prevent persist error over the time. And lastly, for the PID controller, we can expect that for the response, the system achieve faster, precise response with a minimal error and reaching the set point and staying there with all the three parameter, which is proportional, integral, and derivative control. And for oscillation, we can expect the derivative action help to reduce overshoot, so oscillation are minimized and quickly down. So summary of our expected result based on the Cohen-Kuhn table. So we can expect for the P controller is a good response but possible steady state error. So useful where a slight drift is acceptable. For the PI controller is improved accuracy with reduced oscillation, better at correcting a steady state error. And lastly, the PID controller, we can expect the precise control and minimal overshoot and stable response with fast settling time suitable for complex process with delay. So in each case, the Cohen-Kuhn tuning wheel table aims to provide a more stable and efficient response by balancing speed and stability for process with time delay. That's all for me. Thank you.